CEO Augsense Labs. Welcome, sir. Mr. Ramesh Kumar V, co-founder Grahaa Space. Well, welcome, sir. Mr. Suyash Singh, co-founder and CEO GalaxEye Space. Mr. Rakesh Bhan, AVP Satellite Operations at TASL. Welcome, sir. Thank you everyone for joining and I'll hand over the dais to the session chair, Shri Somya Sarkar, sir. Over to you, sir.
First of all, very good afternoon to all, and I welcome all the panelists who are here sitting on the dais. And as you told, ma'am, the topic for today's discussion is advanced remote sensing payloads. So, as you are aware, actually, in today's, when you talk about space, you talk about space, you want to see something actually. So these are the payloads are basically eye of any space mission. You come to know that, okay, what is the kind of information that you have, whatever it could be. It could be information coming from payloads, it could be coming from communication payloads, from Earth observation payloads, planetary payloads, payloads for astronomy, astrophysics. It's all actually, the moment you think about space, you think about what's going out there. When you think about actually what kind of information you want to extract and make use of it, it is all about payloads basically. So payloads are extremely important to any space mission. I don't have to overemphasize this fact. Now coming to advanced payloads, I think how do you really define what is advanced? So basically, in my opinion, you all would agree that maybe one way to look at it is an advanced payload is something which gives you probably the best performance in least cost, and probably the fastest possible time. So needless to say that this is an utopia. We all would like to have it, but it's very difficult because everything actually comes for a cost. So I would expect, I don't know, if it's I expect that this would be actually a free-flowing discussion. So if that is the case, let me then set the ball rolling by telling actually, let us look at that how do we define that what is advanced, and how do we ensure out how do we achieve what is advanced. To start with, for example, when you talk about remote sensing payloads, I would go back to that notion of 4 R's. The R's means the resolutions. You talk about spatial resolution, you talk about spectral resolution, you talk about temporal resolution, and you talk about radiometric resolution. So we are always striving to improve these 4 R's actually. Spatial means actually you would like to see an object as small as possible from whatever be the designated orbit actually that your satellite is in. That can be 400, 500, 600, 700 kilometers, or maybe even from geostationary orbit of 36,000 kilometers. So what is the smallest distance or smallest object that you can see, which basically defines your spatial resolution? Your spectral resolution, basically actually that how distinctly actually that small wavelength content you can decipher. So basically how many number of bands you are having, what is the bandwidth or the spectral resolution you are having. Then when you talk about radiometric, that is actually what is the smallest change that you are able to see in the reflectance of the object. Then obviously actually the noise of your system comes into picture, that it has to be above your noise floor. So these are the kind of some of the considerations. Then temporal means actually would like to cover an area as many times or as fast as possible. So there actually it comes the coverage, that how big is actually or how large is your coverage. And these are some, for that matter, if your coverage is smaller, then how often you are able to revisit it, that is actually go for a platform or satellite which has agility. So these are some of the things actually, and I don't have to again actually tell who are working in this field, they would be knowing that all these things are actually in conflict with each other. For example, when you talk about smallest or the highest spatial resolution or the smallest object that you want to decipher, your coverage becomes smaller. So your swath or temporal resolution suffers. So like these are some of the aspects I expect that today actually we will be touching upon, and also actually about the future trends. What are the future trends actually that be it small satellite constellations, or be it about bringing down the cost and the developmental time, or be it about actually extracting, because it's not about actually the data, it's about the information. So how many bits per information? These are the kind of concepts that I would request our panelists to touch upon. And of course, actually, besides the optical payloads, let us actually also look at some of the upcoming, or I would say the novel concepts in SAR technology. Concepts like, for example, my expertise, of course, in optical payloads, but I know I have heard of terms like actually multistatic or mirrored SAR for that matter. Geostationary SAR, this thing people are talking about, it is extremely challenging, I know that. Then of course you have small constellations in the optical domain, you have optical payloads. But of course you are now having actually people talk about constellations, or in fact they are putting constellations in SAR as well actually. So these are some of the topics we should be touching upon. Of course these are my just some limited views that I expressed, and I would expect that all our panelists will have their own opinion on these topics or any other topic related topic in this domain. Thank you so much. So shall we then start the way like the way I presented some of the points? So do you have something to add? I think it will be better that let us actually, each one of you, give your views on this topic first.
No, first of all, sir, thank you so much for a wonderful introduction on at least that word advanced, right, which is very important to be ironed out, and the way you articulated about the 4 resolutions is very important. So let me start with my introduction. I am Suyash. I am one of the co-founders and CEO of GalaxEye. We are a company based in Bangalore, a space startup. We are building a very unique satellite consisting of a multispectral imager as well as SAR on the same satellite. And this is primarily something which I would kind of get started as an advanced payload in the Earth observation context. For us, I think it starts with use case, right? Because we are not the technocrats who have worked for 30 years in the industry and whatnot. It always starts, from where probably we have found some of the problems to be solved in the industry. So simplest problem for us that came through was I don't understand SAR to analyze it or to put a computer vision model on top of it. Right? Although SAR is one of the best data sets, can see through clouds, it can do nighttime imaging and whatnot. But I can't really upload it on GitHub, and we cannot open it up to some thousands of developers to write a code on top of it and identify a vehicle or whatnot. You really need experts like Sir and Rakesh and everyone for that matter. So we thought, there has to be a better way to visualize those SAR images. And that is where this concept came of optical and SAR coming together on the same satellite. So we want to really generate, so as one of the words that you might have heard very constantly in the last 1 year, so we are generating an optical SAR from SAR, generating an optical image from SAR by the kind of satellite that we're building. So it's a generative AI kind of effort. The simplest way to think about it is this. So we want to ensure that anyone and everyone who's trying to acquire a particular imagery from space utilizes it for whatever applications they're trying to do that. Another analogy to take, the 12 months of the year, for 4 months you don't have an image because of the clouds. And if you're monitoring, and if you have built a software as a service solution, that takes in imagery every week and give you some insight on top of it. For 4 months, it is cloud. So your automated application is stopped. So if you think from that perspective, the consistency of the simplest applications of the satellite imagery is at question. And that is precisely the problem that we're trying to solve for the consistency of satellite imagery, right? Of course, what you compromise there are certain things that you compromise on. You cannot recreate spectral signatures from SAR just like that, So maybe there are some limited use cases on that, but certainly you can recreate spatial resolution level object detections, and you can do a bunch of things there. So that, in a nutshell, is what we are trying to do at GalaxEye, and we've been fortunate to talk to a bunch of customers across the world, and it seems like this is one of those genuine problems that they face on a daily basis. Because on the downstream, people are trying to develop applications, and when they start to develop an application, they bump into this consistency of the problem. They may go to Sentinel-1, Sentinel-2 for a coarser resolution data set, but then they don't know how to decipher SAR properly, and multispectral is 90% cloud cover, 12% cloud cover, or 50% cloud cover. There's always a challenge. So happy to answer any questions on top of it, but that's where I will start. Thank you.
Thank you. And thank you, sir, for starting the session with the good notes of and setting the ball rolling. And thank you, Suyash, for touching upon a few things from GalaxEye. I am here from representing Tata's right now here, Tata Advanced Systems. I'll briefly touch upon what we are doing, and also try to complement certain things what both of the gentlemen actually touched upon. So Tata Advanced Systems have recently entered into the space business with a vision of 10 to 15 years. Tata Advanced Systems entry is something from the bigger segment to the space sector. We have not seen this from last 4 years when the space sector started transforming in India. So Tatas are the first ones to enter into the space segment, and that too quite fast. So the first thing was to set the system right inside Tata, because we have our own inertia, because we are not a startup. We have our own engineering-based infrastructural stagnance sort of thing in terms of we are horizontally spread. To make it agile is itself in a big hurdle in front of us, which maybe Suyash will not be facing. So there is a process already inside the company. So we have to comply to those processes. But at the same time, space is very challenging in terms of getting the new technology, and setting this complete process inside the company was our challenge. So we did a project fast, that's TSET 1A. We had to find a technology provider for that. And it was just within 7 to 8 months, we could launch that satellite from the scratch, making a lab, making a class 7 lab integration, setting the teams right, and launching it. And now this payload was the spacecraft was launched actually on April 7th. We're in the commissioning phase. By the next month, July 3rd week, we're expecting that we'll have a calibrated image. And we're setting up a mission control center where a lot of other plans rolling out. And you may not find it freely on the web or somewhere what Tatas are doing. That's the other story that I will not touch upon here, but that's the way the Tatas work. So coming back to what is the remote sensing challenge right now, as Suyash touched upon, and what we are trying to solve. And upfront challenge, what you see may not be actually what actual challenges are. Like the optical satellites, the challenge is not only to capture an image through the clouds, because if you go into an aircraft, you will see you'll see all the clouds. You can imagine how a satellite will take an image from 500 kilometers or 400 kilometers. It's 99%. You will find some cloud patch in the image, even if it is clear, or you will find haze. So corrections are there. When you talk about the other challenge is where you want to take an image at what point of time, whether your satellite is there or not. And if an user comes to us, typically from the strategy community, that we want an image of a particular day. Suppose Delhi, we want an image from tomorrow morning at 10. I may not be able to satisfy that requirement with one satellite or two satellites or three satellites. I may need a full constellation. You can imagine the cost of that. You are buying one image of maybe 5 kilometers by 5 kilometers or 10 kilometers by 10 kilometers patch. What it takes, the infrastructure wise in the space to take that image. Now, when previously I was with ISRO for two plus decades, 22 years almost, and Sir knows me very well. It was from optical side, I was from remote sensing, synthetic aperture radar systems guy. From the classical industry of NASA, ISRO, of course I was with NASA also for 1.5 years in California, but the process is the bigger satellites, very efficient bigger satellites. But that doesn't satisfy the problem I pointed out right now. You want a Delhi image tomorrow morning at 10 o'clock? We'll be lucky to get it tomorrow if one satellite goes over it, but otherwise. So the customers have become smarter. The problem statements have become smarter. The solutions also have become smarter. So we need to see that how do we put tens of satellites to be everywhere on the earth. That's how the communication business transformed. From the bigger satellites to Elon Musk's new constellation of thousands of satellites. So at the same point of time, we have to see how the economics works with this. I may see that I'm looking at everywhere on the world. Now I have 20 satellites, 30 satellites, or 40 satellites. Is every pocket giving me the returns for that investment? So that's where another challenge is. So these are the background problems. Upfront problems are like whether we're able to capture the image or not, but the background problems are for a business to sustain. There are a lot of other things too that we are struggling with. Now, if you see the longer term plan in terms of what we should be doing, so the technology is again, coming in front of us. That what technology we should be using to bring down the cost. Finally, it boils down to that what every patch of the image that we are selling at what price, and the prices are also coming down. As I was telling yesterday in a panel discussion that I was in a panel discussion for the smarter satellites. I mean, what is smart? Smart is not, it's a referential definition. Like today, what is smart may not be tomorrow smart. So it's tomorrow's smarter definition is different. So we have to be always smarter, one step ahead from the customer point of view, from this economics point of view, to find a solution that how do we provide it at a cheaper rate and at the, to some, I will not say only the price, but there are strategic communities who are able to give it a higher price, but again the timing comes in picture. Synthetic aperture radar is still a niche, technology in the public domain. I'll say everybody is not able to make it, but at the same point of time, whether the economics works for making that synthetic aperture radar from the scratch, supply chain plus talent and everything to maintain it. Fusing the data is another problem with the remote sensing. This has been going on from last 5-6 years. Like we talk about ARD, analysis ready data. Fusing an optical data and hyperspectral data may be easier than fusing an optical data with microwave remote sensing, synthetic aperture radar data. The problem is not that we don't have the same resolution. The resolutions have improved. Now we find synthetic aperture radar as an X-band, less than a meter resolution, 0.5 meter, 0.2 meter resolution. Recently there was 0.13 meter resolution, the highest bandwidth for 1200 megahertz, which can be used by an American company. Resolution is not a problem, but the problem is the nature of the remote sensing image in optical domain and the radar domain is different. We're talking about the RCS grid and then we're talking about the optical grid. This problem is still with a lot of engineers to solve with that. How do we normalize the two images before we fuse it? So from a customer point of view, that is a hidden problem. Because, the customer wants a fused data. So the background, the technology barriers are there. Other problem is that how much computing power it requires, whether we should put an edge computer there. Till now, there are synthetic aperture radar processors on board which are very, very costly, very, very high computing power it requires. So we are not able to solve those problems right now. There are often problems with us. The optical size, suppose we talk about the smarter satellite preset 1A, we get a thumbnail, and then a customer decides whether we need to download it or not. So we are trying to cut down on every bit of the cost that it requires to bring down the data. If we say that it's not a good image, there was a cloud patch, or it is not a good image to download because it was wrongly projected somewhere, we don't download it. So we save on the cost of download. So every bit of the data is actually being, every corner we are trying to save. That's how we become smarter in operations. And if you would have seen 10 years back mission control centers, those used to be actually the bulky computers and a lot of people working there. Now you find on your laptop, you can operate our satellite TSAT-1A right from here with a web page. That's what the smarter solutions have come. And the dashboards have become very smarter in terms of operations. It's like, everybody can operate a mobile phone like that. We have made the dashboards. So this is, yeah. Yeah, so I was just telling about some few problems and so much solutions to it. So let me cut down on my this thing. Will come back to please.
Thank you, sir. I am Kannan, co-founder and CEO of Augsense Lab. We are an advanced RF remote sensing sensor manufacturing organization. So let me start with the where Suyash stopped. He presented the value of multi-sensor satellite. So how Augsense Lab started its journey is, do we need multi-sensor always, or can we extract more information from the same sensor? Of course, optical is a different playground. So how we were developing it is if you know how to build an advanced RF sensor, which can relay multiple frequency band, then it can same time capture signals for synthetic aperture radar, same time it can act as RF field and even radiometer also. So what will happen is currently, suppose if you wanted to develop a mission for maritime situational awareness, you wanted to look for signals coming from threat vessels. That time you wanted an image of that, and if you wanted parallelly one RF satellite, one SAR satellite has to be there in that region of interest, then that mission will become costly and almost impossible to implement also. So you have to look for multiple data sources. So how Augsense Lab is thinking is in two ways. One is building an RF sensor which is powerful enough to detect weaker signals so that you can do advanced signal processing to get the result of RF field or synthetic aperture radar. Second is, do we always need an active synthetic aperture radar? Because when you have active synthetic aperture radar, that means you have to emit. That means you need to have WPC approval in all the countries. Suppose that frequency band in India may not be valid in China or in Egypt, that is. So utilizing the signals of opportunity already existing, like a L band or KU band, because that intensity is increasing because of the communication revolution is happening on, can we create the image? So in Augsense Lab, how we are trying right now is we are building a quantum enhanced, we are utilizing the potential of quantum sensing to detect weaker signal, which in turn creating a new payload concept of synthetic quantum enhanced passive SAR and RF field. That's a short introduction of what we do. Maybe we can answer any question.
Thank you, Kannan, and thank you, sir, for providing the opportunity here. So I am Ramesh Kumar, co-founder and CEO of Grahaa Space. So we are into streaming near real-time videos from low Earth orbit using our own constellation. So it all started with the NASA's high-definition Earth viewing experiment, which ended last decade, wherein from ISS they were trying to stream live videos, and there were several challenges that was posed, and it has been well documented as well, and that's where that was the spark. And so what we felt was all the geospatial data that we are seeing right now, it's all static images, old, and the real time was not missing, was missing actually. So then we went and spoke to a lot of people around the industry, and what we figured out was real-time geospatial data could be useful for a lot of applications, on-ground applications, including military missions, disaster and emergency response, and border monitoring. And there are tons of other applications as well. But then, based on the HDEV itself, there are a lot of challenges in streaming near real-time videos from low Earth orbit. So that's what Grahaa Space is intending to do, using our own constellation, which will communicate with each other and also stream live videos regardless of whatever satellites watches the ground, right? So, basically, adding to the challenges with the other fellow panelists have mentioned, static images itself has been a challenge, sending it real time. You don't get it as Rakesh had rightly mentioned, and you need it the next day. It's going to be a challenge. So then video is yet another level of challenge. First thing is capturing, then streaming. So that's what we are working on. Hopefully, we get the technology demonstration done this year. So thank you.
Yeah, thank you so much. Actually, so many interesting points came out actually during the discussions, the brief discussion that we had so far. Already, some of you talked about optical sensors actually getting affected by the presence of clouds. So, of course, that's an issue actually with clouds. That's where I think SAR imagery is of extreme utility, I would say. But then SAR has its own actually. I would say that its own complexities that one has to sort of deal with. When you talk about actually dealing with, let's say, the issue of this cloud, so you have actually people talk about use of AI/ML, and so that your sensor are basically equipped with this power or this capability of cloud detection. So you have a sensor which basically actually detects the clouds. And as per that, either if let's say the scene is infected by whatever, you can always fix that bar. I would say that let's say more than 50% or 60% is cloud infected. So you would not carry out the imaging, thereby saving your resources. Or else you can always actually the remaining 40% which is not actually infected by cloud, which is free from cloud, only that portion of data is sent back. So of course actually that will call for some, building some kind of intelligence into a sensor. So this is one way to go about it. Now, when you talk about smartness, so it's usually we tend to sort of attach some kind of artificial intelligence to it. Actually, okay, my sensor is smart means actually it can take its own decisions, or at least a part of it. But I would say actually let us go back to the basics as well actually, and then address this question that whether the sensor or the satellite is actually doing the job it is meant to do. It means does it have the feature which is required for a specific application. For example, we talk about actually it's a very commonplace thing that we tend to associate again actually very high resolution advanced satellites or advanced optical sensors with something which has very high resolution. When you talk about 0.3 meters or 0.2 meters, means it's a very advanced optical sensor. But I would say actually that's a misnomer actually, or it's a misconception. Reason being, it is basically actually an advanced sensor. It's a very capable sensor for certain applications. For example, you want to use it for urban planning, yes, you need 0.3 meters is always an asset. But however, if your applications are related to resource monitoring or, for example, agriculture, or crop estimation, crop acreage, etc., you don't need 0.3 meters. So you have to be mindful of the fact. So that's not a smart way to deal with it. Simply actually to kind of actually brush everything, paint everything with the same brush. So that we have to keep in mind actually. So smartness, for that you have to actually marry the application or marry the features of the satellite or the payload with the applications that you are basically seeking. So that's something actually. Then again, actually, one important factor about your smartness is that how much are you getting out of the satellite or out of the sensor? It's not always that you need all the data. You may be generating a lot of data. For example, I'm interested in just finding out some change actually. Something is moving. Let's say in a landscape, you may have trees, you may have houses, you may have fields, so many things, so many features, but you are not really interested in, in that. You are expecting some event to happen, some event, and you want to detect that event. That event can be anything. It can be movement of vehicles. It can be like some forest fire or something of that sort, some celestial, some natural hazard or that is taking place. So for that, you need not every time actually acquire the full image. Why do you need to do that? So every time like continuously acquire the image and then you compare the image and then make out that yes, some movement has taken place, something has moved. Instead of that, you actually concentrate only on that part. Actually, you might have heard of something like neuromorphic imaging. It is something like which mimics your brain actually. Like you always have this peripheral sense. There's so many people sitting in this hall, for example. You're not always actually, like every time looking at everybody. But the moment somebody enters or the door opens, immediately actually you sense it. The brain actually reacts to it. So it is that kind of intelligence or that kind of smartness you have to build into your sensors. And only actually that part of the data, which is basically data is again actually data per se has no importance, I would say, no significance. It is the information which is important. So basically how many bits are you utilizing or how many bits are you consuming per information? That is extremely, extremely important. So of course from these things I am picking from your discussions only. So these are some of the points that I picked actually. I think somebody mentioned about quantum enhanced sensors. Yeah, that is again actually a very important, I would say a very important point, because in today's world with quantum technology actually going by leaps and bounds, and our government also actually spearheading this of quantum frontiers, where actually they have already identified some 6-7 different topics in the domain of quantum computing, quantum communication, etc. So this is something actually we have to be mindful of, and of course, like you said, actually sensing this improves, or I would say actually multiplies the capability of sensing manifold. So that's again a relatively new field, I would say, but it's a very potentially very attractive field. Okay, I would like actually all of you to address this question of reliability. Now, space, as we all know, we have this notion that space is extremely unforgiving, that you don't get a second chance so far as space is concerned. On ground, you can repair anything. If something is not working, you can fix it. But if it's already gone to space and it's not working, it's extremely difficult. I mean, it's not that people are doing these days actually. You have on-orbit servicing, etc. Such kind of concepts are there. But then these are extremely expensive and also technologically very challenging. So reliability is always a question actually. That okay, whatever we are sending up there has to be fully tested. We have to be absolutely sure about it and all that. But however, in recent times, that is getting actually redefined, I would say. Now, you might have, I don't know, many of you actually would remember that sometime back there was a launch actually by SpaceX, and the rocket actually on the way up, it exploded, and people who were sitting in the mission control room, they all clapped actually. So it was a bit bizarre that okay, something exploded, something got destroyed, and everybody clapped actually. But later they explained that why they clapped was that because they tried out certain new things. Their objective was that okay, if something failed, it should fail early, so that if they know about it and then they correct it. So basically, just look at the paradigm shift actually in thinking that okay, you are building something. You are building it many times for that matter, and you want, at a cheaper cost, newer technologies, and you would actually, you expect that it may fail. But if it fails, it should fail as fast as possible so that you can immediately go back to the drawing board and correct it. So these are some of the concepts which are, as I said, actually getting redefined. So because many of you are actually from that corporate domain, I would like to have your views on this particular aspect, that how do you look at it actually, this particular area of reliability? Maybe I start with the same sequence, Suyash.
Sure, sir. I think a couple of comments maybe before I come to your question. the way we think about many technological aspects, I think we all are engineers, and of course, we, we we have esteemed scientists in the labs, and ISRO and all the esteemed labs of the country. I think engineering problems of bits and other things, and putting an RCS onto a pixel can always be solved. But the problem is, what is that we are trying to solve? So even if between the clouds you have some portion to capture, from technology aspect, I guess I can capture and I can give it to someone, right? But the user has something that they want every week. And if I go and say that today you have 1 square kilometer, tomorrow I'll give you 100 square kilometer, and day after tomorrow I'll give you 50 square kilometer, they don't really care at the end of the day, right? So my humble submission onto that is very simple. Right? So technologically, we tend to make things more and more complex as we go on, and I am probably one of the least qualified engineers on the panel. But what I feel is that at the end of the day, if we really need to commercialize this opportunity, we have to think through the most usable solutions to the final user. Now, there have been cases, in the past, which, there were a bunch of myths that you cannot do A, B, C things. And ISRO has proven time and again that these can be done. Chandrayaan is a great example of that. SpaceX is a great example of bringing the launch vehicles back. So, things may look very difficult today, but maybe with all of your support, everyone's support, it can happen. Why it needs to be done is to solve a particular problem. That's the right way, rather than that, okay, I can do A, B, C thing, so I'll do the D as well. Right? So that's probably a couple of comments before I go on the reliability aspects. So in terms of reliability, again, as I said, I'm the most least qualified engineer on the panel right now. I'm not involved much on the reliability testing in the satellite in my team, but we are definitely trying to take a lot of help from InSpace. And we're trying to use whatever has been established. We're trying to follow the guidelines as much as possible.
Talking about the approach, actually, the approach to it, actually, that okay, I'm putting it actually something on space. It has to be absolutely, I'm damn sure about it. So whatever it takes, actually, in terms of putting in time and effort and money, actually, is really worth it doing it. Or there is another way, another school of thought which is coming up, actually, that okay, don't worry too much about it. You make, actually, instead of the one, you are making it anywhere 10s, 20s and 30s and 40s, actually, such things, such kind of systems. Even if one of them fails, you are going always ready to put up another one, actually. So that is the kind of thing, actually. So that is another way to look at it. So I was just thinking about, in case if you have anything, maybe you can have.
No, I completely agree, sir. I think we will probably have to find a midway. We can't keep launching satellites and find out. We might have to come up with some simulated efforts in between, and understand how to make sure that our reliability development cycles are much lesser and optimize it ASAP. So that's what I can say. But definitely post our design, expert reviews are the most important thing that we want to go through generally, and also taking a lot of support from InSpace in that sense. I'll give it to Rakesh.
Yeah, thank you, Suyash. As Suyash rightly mentioned, reliability, I will see that reliability in the new space companies doesn't come on the first day. There is a process, the quality assurance, quality control. The process comes later in this life cycle of making a satellite outside, other than the ISRO one. Because I'll say ISRO, NASA, other centers like AFRC have worked with different agencies to see that reliability and quality aspects are not imported things. These actually built as the organization builds its own process and steps and learns from the mistakes. There are standards, there are ESA standards, NASA standards, and ISRO standards. A lot of things have been, time and again, they have redefined these standards. But at every point, when you come into the quality aspect of it, in terms of reliability, making it damn sure, it adds up to the cost. So I'll quote you an example in remote sensing. When I was working with Dr. SSRana, our earlier boss, He quoted me an example that, it was one Russian scientist who was visiting NASA, and he said one RF amplifier, which was around 120 kgs in Russia, was around 5 kgs in US. He said, how do you make it so small? And this is, but it was 5 kg was costlier than the 120 kg. So the answer simple was this 5 kg from 120 kg, all the cost has gone into the reliability of it. To make it damn sure that Russians didn't care at that point of time. They said, whatever it takes to make it work, don't worry about that. So this is how we see the reliability adds up the cost, but it makes things more sleeker and better way of, so that we can handle it. In the private space, the companies who have already launched few satellites, they have also been testing new technologies before it goes to the space. So they try to reduce this cost of adding the reliability. So I will quote an example of a recent company who contacted me in my private way of consultation terms of things. They wanted some opinion about their wheels have failed. So they were struggling for 3 months to see what has happened. So finally they found out, how this reaction wheels are something which always keeps on rotating. So it is more of a reliability. Then I asked for what is the reliability report or endurance report or from the company who you source these components from. I was surprised to see the process doesn't exist, although the company is 5 years old, 7 years old. In fact, 5 years they have been launching satellites, but this process did not exist. But the first thing I asked them, why don't you introduce this process for the future satellites? Immediately the cost went up by 10% for the satellite, the next satellite. This is what it costs outside. So talking about reliability is actually very premature for these 200 odd companies we have in India. But I wish the process comes at a very lower cost adequate. At the same point of time, I will tell you, material science has become smarter. Today, we can rely on certain materials not to fail in space. And EMI, EMCs, all those components, red hat component definition has changed. So that has also made things more reliable in outer space. I will quote Sarkar. Also remember that when the concept of Dr. Kalam actually tried to make one satellite with one university, and when the proposal was floating in ISRO for something, I don't know what was that reason why it came to ISRO for. And we said, no, it's not going to work because we came from the highly reliable process. We said, no, it's a commercial domain, they are using commercial won't work. But that satellite worked. So this is something that you do smart engineering, the reliability will take a back seat. So this is my take on this. Thank you.
Thank you, Rakesh. Before we move forward, I just would like to just know from the organizers, how much time do we have? Pardon? 10 minutes more, okay. Why I raised this question of reliability, because it has direct bearing on your cost, your efforts, your time, and if you have to be commercially viable, this is something actually you cannot ignore. At the same time, it is always a catch-20 situation because it calls for investment. It calls for investment. In building these infrastructures, and of course, actually the testing time, the time and the money associated with extensive testing. So that's why your views on this.
I do not have any additional thought other than mention. But when Sir was mentioning about the SpaceX scenario, I was thinking that soon Indian startups also have the privilege of having failed mission, and that will get clapped.
Okay, so for the proprietary payload which we are building, there are rigorous tests that we are working on and hoping to ensure that we get a 98% success rate in terms of streaming videos. The thing is, cloud cover is another important thing which has been already stressed upon. So that's one of the most important things we wanted to be relying on to ensure that our AI algorithm which sits on the board clears it off and by referring to the archival image. Overall satellite itself, so that tests have been put in place and already BAS standards have been released, and that is what we are following. Earlier they were NASA standards and recently the BAE standards have come forth. So that's how we are approaching it, sir, in terms of reliability for the satellite as well as for our optical payload.
Thank you. Right in the beginning, actually, somebody talked about the importance of having constellations. Because if you want to see, let's say, a particular place, actually a particular area, a particular region, and maybe you want to see it anytime, or let's say, actually, for that, let me come down one step below, one step down, that you want to see it every day, for example. So obviously you cannot do it actually with a single satellite, or you need to have a constellation. But the moment you talk about constellations again, you would be looking at something like a constellation of small satellites. That's what comes to your mind, because otherwise putting up a constellation is always a costly affair. And again, actually costly, I'm telling actually because other technological issues are anywhere there. So, but again, to be commercially viable, cost is an important factor. So from that standpoint, I was referring. When you have these small satellites, actually, then sometimes your resolution, for example, suffers. You would be, you cannot have, for example, if you want actually 0.2 meters or 0.3 meters class of images, you cannot actually get that, let's say, from a nanosat or from a microsat. It is extremely difficult. It's not. So what do you do in that case? Okay, you get 2 meters data, or maybe actually 1.5 meters or 3 meters data coming from small satellites. So your resolution then suffers, or there is compromised. Whereas actually you have this coverage actually as fast as possible. So maybe then the way forward is that you go for constellation of very high resolution satellites. So it's a big satellites, constellation of big satellites. So again, actually that's going to be a technologically challenging as well as actually a costly affair. This is something, anyway, I think you people might have heard about that Albedo mission, which they are telling actually by 2025 they will be launching optical payloads having resolution of 0.1 meter, and by 2028 they will be putting up, I don't know, some 24 or 40 satellites constellation. So is that the way forward? And if so, then actually in the Indian context for the Indian startups, this is something actually we have to look at, because there are so many other things associated with it in terms of resources, in terms of money, etc. So this is something, I don't know whether any one of you would like to comment on this particular aspect.
Let me comment one thing on this. Just to answer simply that when we talk about smart engineering in terms of the resolution, in terms of what we can achieve with the small payloads. Today we are talking about 0.7 meter resolution, 0.5 meter resolution from a 50 kg payload in the same orbit of 500 kilometers. How that has been possible? There are multiple things in it. One is how do we step and stare in terms of our piezo sensors, patented technology, how do we do step and stare to increase the exposure time. At the same point of time, what happened was when we classically tried to solve the problem of having high resolution, we were limiting that point of time what type of sensors we are using on the back. Then everything comes down to the optics, that we have a larger optics. Now, if you want better resolution, we'll make it bigger optics, and so that it focus the smaller area. So the swath gets compromised. Then at the same point of time, it becomes larger telescope. Then we go to cassegrain, then we go to mirrored structures. So those are the classical way of looking at it. Now, when you talk about the smart engineering today, we have 0.5 meter telescope, 350 mm aperture, 0.7 meter native resolution from 500. So how that has become possible is we're talking about 7 kilometer swath at this with the aperture of 350. So these engineering problems have been supported by the technology we have available today and the way we are looking at it. Our time saw that with piezo, we never thought of we'll fly piezo with this keeping this step and stare concept live in space and solve this with the smaller satellites. We never thought of that we will use such small aperture and we'll get those that efficiency of those the mirrors, the surface treatment, everything which happens in India now. So engineering has technological advantages has supported us over the time. So smartness is already, we have to patch up these solutions together. It's not like we become blind to it and we use the classical solutions. So that's where we have to be open of for the new age solutions to it. Now, when you talk about this 0.3, 0.2 meter resolution image, again, sensor technology has to catch up with. That's what the profile of technology upgradation in this space next 2 years, 3 years, what is going to be available. So we start engineering today. So that's how we solve the problems, but there's nothing, no magic in it. So
yeah, absolutely. I mean, you have to rely upon, advanced image processing techniques. For example, you cannot actually leave it only to the hardware. At hardware level, you actually, you achieve it. You will have to actually, hardware will have its own limitations, but you will have to actually rely upon what you do finally with that data actually. For example,
right.
You may have lower spatial resolution, native resolution I'm telling, but however using super resolution, you can always
exactly. We use the super resolved image. We use from 0.7 to 0.5, and we can still super resolve the better thing. But that has become possible only when we have better sensors, so that we have captured the native resolution with a very good sensitivity. At the same point of time, the smarter web operation, we are trying to use the weather models to find out the percentage of, I will say, what is my success percentage in terms of capturing that image at a particular area. If the weather model says there are multiple inputs to the weather model, it's still evolving, it is still being refined. If I want to if you order an image from the dashboard and say that I want an image of suppose Delhi tomorrow, and weather model says that there is an 80% chance there's going to be a cloud over that area, will not waste the, it will take up the next task and say the user that tomorrow it's not possible because of certain reasons. So then there is a threshold. So smarter web operation has also helped us. So when you have 10 satellites, 15 satellites, and you save 80%, 90% time on the satellites to do a better job, of course it pays off.
Yes, sure.
In terms of, we need not always plan only for satellite missions. So basically, if it is a strategic mission, we should select a combination of drone, apps, and satellite, and the sensors we use in all these things should be complementary. It should be suitable. And I agree to your statement of resolution is not always important, particularly in the strategic area where suppose you wanted to locate a vessel, you wanted to measure the length and breadth of a vessel, but the more important is the positional accuracy. Whether are you able to give a confidently with 1 meter vessel accuracy that a threat is coming from there, then you can be prepared accordingly. And change detection is important. Not always resolution is important. But swap, if you can find a way to increase the swap, it will increase the effectiveness of mission because we can reduce the number of constellations or the satellites accordingly.
So adding to Mr. Kannan, right? So for us, we are targeting 25 kilometer by 25 kilometer is the time which we would be covering, and since it's a video. So the efficiency is more for the video part basically when the swath is high. So it's not just the resolution, as he rightly said. I mean, not just from the satellites, but we are also planning for augmentation of this data along with the drone data as well as with the hierarchy problem. Not just the hierarchy problem, but then drone. So that is the only way in which we will be able to provide useful applications to the customers as per their requirements. So that's my take on short and sweet.
Thank you. Yeah, I think there was a question from someone raised hand. Yeah, please.
Hello, good afternoon. I'm coming from the investment community, and so I'm curious with the turnover of technology, what's the rough time period between when you need to make upgrades to the satellite or to constellations? Is it a 5-year turnover? How long should the ideal mission life be? My corollary question would be, how much of that can you do through software upgrades as opposed to hardware upgrades? So if I'm an investor and I'm looking at various deal opportunities, and someone brings me a constellation that's going to last 10 years, but should I expect that they're going to be outmoded and relegated to second-tier business? after 5 years or 3 years? How quickly is the turnover rate in technology to maintain cutting edge from a business point of view?
I just would like to say actually, if I understood your question correctly, you're telling actually that, I mean, what would be the time period within which you would like to upgrade, or actually, in view of the changing technology, like today, what is relevant may not be relevant actually in, let's say, in the next 2 years, 3 years, 4 years, 5 years time frame. So how often would you like to upgrade your let's say the hardware that you have put up actually up there in space? Is that actually what the question?
Essentially, but looking at it from a business point of view. So somebody is going to, if there's new technology available, somebody will deploy it. And as long as that technology captures the market. So from a business cycle point of view, what is the ideal time frame? Apple, for example, with phones, upgrades roughly every 2 years, right? And they force the competition to match accordingly. So in this sector, because as you elaborated through your discussions, sensors and other things are evolving at a reasonably rapid rate.
Yeah.
I think you said every 2-3 years.
Yeah.
Or it takes 2-3 years for the new technology to make its way forward. How quickly does that mean that your constellation or your satellites need to be designed for obsolescence and replacement?
I think actually I would say the typical lead time would be from the design to realization, typically 3 to 4 years. 3 to 4 years actually for, I would say, for state of the art system that can be built actually. So that kind of capability exists, but however I would like actually, because it's more actually the commercial domain.
Yeah, it's a commercial domain.
Yeah, so maybe Rakesh, you can address this.
Yeah. So your question is right in terms of business point of view. How do we decide on right now what we are putting in space? How do we make it viable? And what point of time we should upgrade? So let me tell you simply. If you have asked this question, if you would have asked this question 5 years back, I would have tell you this is typically 5 years time frame, the deadline there. Anything beyond that, sustain a satellite in orbit is a plus point that it will pay off us somewhere. But 5 years was the threshold. Now that has come down to 3 years actually, typically for a business cycle. We will like to see that there is a new satellite. We will make all the plans to have a new satellite at the same, in the same orbit after 3 years of its lifespan, and we'll make all the plans according to that. Why? There are multiple reasons for this. One is that a technological upgrade, which may not be relevant after 3 years. Second thing is that when it pays us back, when the satellite is in orbit, when the cycle of that payback, it becomes, our Excel sheet becomes green. And we say that this satellite is plus now, it has given its complete life cycle to us, and that's typically 3 years threshold line for all the small satellite business right now. But different media.
I would also like actually I was just adding that.
No, I was another parameter is the replacement cost. So the launch cost is considerably reducing. So after 2 years, maybe it would be wise to launch a new satellite with a new capability rather than maintaining the old one. So that will eventually, and when the satellite manufacturing comes in the future, we do not know how to imagine things that.
So typically the constellation as of now, especially talking about the low Earth orbit, mini satellites or the nano satellites, 3 to 5 years you can say that comfortably, but it also depends on a lot of other variables like the application and then what orbit it is sent into, who sent it, and then whether it has lived to its expectations and you have had the ROI of it. So a lot of other variables also come into picture, but typically 3 to 5 years as of now, as he already mentioned.
Thank you. I think we have. Okay.
India is mostly known for making devices cost effective, right? So I would like to ask is there a trade-off in quality? If I must say, like making it cost effective. Like let's say Apple phones are very priced, and they maintain the type of software. That software is like pretty much rigid, and you don't get lags or anything. So the thing is that if we are talking about space, it's like a satellite has minimum 5 years to its lifetime. Just giving an example. So is there any trade-off of quality? If
Quality with cost, is it?
Yeah,
Is what is
quality
the question?
with cost. Yeah.
No, that's what I think we just little while back we tried to address that question. That the question of quality means actually that is directly also related to reliability. So I mean, so whether that needs to be redefined actually, that like again I said actually space is very unforgiving. So once you send something up there, it is inaccessible to you. If something goes wrong actually and it's not working, then basically you have wasted everything, your time, effort, money, everything. So that way actually quality is extremely important. But then again actually suppose you make a really a very sophisticated system, a big system, and you are putting it up there, and if something goes wrong and you lose that entire year, so it's like actually like you have lost everything. But however, suppose just imagine the same thing is being now being done with 10 smaller systems and one of them fails actually. So basically redundancy not at the hardware or the instrument or the satellite level, but redundancy at the mission level or at the constellation level. That is the kind of like a approach that many these people are taking now, actually new startups for that matter, or I would say commercially actually companies which are operating, they are taking this kind of approach, wherein actually the same activity is done by smaller units, and even if one of them fails, you are always actually ready with the penalty of cost, time and effort actually is much less as compared to like one big system that way. Any other question?
Thank you very much, gentlemen, for this incredible session. And thank you very much for your time. I'd request our session chair, sir, please present a memento to our panelists. To Mr. Kannan. Thank you very much, Kannan sir, for joining us today and sharing your expertise with all of us. Mr. Ramesh Kumar V. Thank you very much, sir. To Mr. Rakesh Bhan. Thank you, sir, for joining us today. I request Mr. Rajiv Gambhir, sir, to please join us on the stage and present a memento to our session chair, Shri Somya Sarkar, sir. Thank you, gentlemen, so much for joining us at the last session of track 2. I request everyone to please come forward for a group photograph. Thank you, gentlemen. Ladies and gentlemen, this concludes Day 3, Track 2 of Remarkable India Space Congress 2024. Overall, it was a day of learning, interesting chats, excellent presentations, and of course, plenty of powerful networking. I thank all our esteemed speakers, distinguished delegates, guests, the organizers, and everyone involved in making this conference a grand success. I request you all to please join us for networking tea and coffee, and right after the tea coffee break, I request you all to please join us at the same hall for closing plenary right at 4:30. Thank you so much. Have a wonderful evening ahead, and thank you so much. Looking forward to see you all next year. Thank you.